Dinner at 6.
Okay, as promised, let me say a couple of words about the next homework due, the last homework, I should say. The first one, I was just kind of going to give one of the problems a little bit, so I kind of broke one of the problems up, sort of piecemeal a little bit. The first one is, because I think this is kind of of interest. Suppose you have a ring that's Noetherian, and suppose that P is some property of an ideal that you might have, any property you want. Or suppose P is the property of some ideal, then there is an ideal Q in R that is maximum with respect to having that property. Right. So as you might expect, the ascending chain condition comes in here quite heavily. Number two, show that if R is Noetherian, then any radical ideal is the intersection of a finite number of prime ideals. Actually, I had mentioned to you that something stronger is true for Noetherian rings. That is to say, if you have any Noetherian ring R, and you have some ideal in R, then proper ideal, then there are finitely many primes that are minimal over that. So when I talk about a minimal prime over an ideal, I mean a prime ideal that contains I, and I know such a thing must exist because it's contained in the maximal ideal. And a minimal prime over I is a prime ideal that contains I, and there's no intermediate prime between B and I. There's no intermediate prime, right? Number three, show that if D is a Dedekind domain, then any ideal of D can be generated by two elements. There's a number of tacks you may take for this. I like to think about this in terms of prime ideal factorizations, and maybe localization might help as well. Number four, we did part of we did the analog in class to number four, and the analog was where R was equal to K plus X F square F double bracket X. So we actually did it for the power series. The polynomials is a slightly different approach. One of the big things that made what we did with power series easier was the fact that a power series is a unit if and only if the constant term is a unit. That simplified the discussion there. But here in this ring, you can have something like 1 plus X, which if this were double bracketed, if this were power series, that would be a unit, but 1 plus X itself is not, right? So there's some other stuff you got to take care of here. And finally, number five, show that if D is a square free integer, that should be singular, then the ring of integers of Q adjoined with the square root of D, that is the integral closure of Z and Q radical D, is given by this formula here. So the integral closure of Z in that field is Z adjoined with the square root of D if D is equivalent to 2 or 3 mod 4, and it's Z adjoined with 1 plus radical D over 2 in the case that D is equivalent to 1 mod 4. Now, there's a subtlety that you might think about here. I've seen this done in number theory books, things like that as well. And there's some number theory stuff that you've got to do to sort of verify. Let me point out that at the beginning, the fact that these things are contained in here is fairly straightforward, right? So that should be easy to show. The question is why is this exhaustive? Why is everything smiled, right? And there's some number theoretic arguments that you'll have to make modular with it. It's not too hard. But there is one thing to be careful that's often overlooked, I think, when you see the proof test. Notice that everything in either of these rings satisfies a quadratic polynomial, correct? Notice that everything in here satisfies a quadratic polynomial, correct? Why is it that everything in Q square root of D that is integral has to satisfy a quadratic? Yes, I know it satisfies the quadratic over Q adjoined over Q. It satisfies that, but how do you know that there's not some monic polynomial in the integers of degree 3 or 4 or 5 that something satisfies, right? How come this isn't bigger? How come there isn't something in here that satisfies a third degree polynomial? Maybe in theory, to be monic, it's forced to be a degree 3 if you're going to have monic as the coefficients. Of course, this can't happen, but make sure that you pay attention to that detail. Okay, any questions? So that should be fun. You guys have kept up on the homework probably a bit better than I have with grading, but some of you are still missing some homeworks actually. So just get everything to me by the sooner the better. It makes me happier the sooner. But anyway, this is due. Everything should come into me by let's say noon on December 16th. And if anybody's got a problem with that, then let me know. Okay, questions? Okay. Okay, any questions? Yes, and I should be done with homeworks 3 and 4 this week. I do apologize again for taking so long. Actually, I did some head counting. I have written letters of recommendation for 28 individuals since the summer, so that's slowing me down a little bit. Okay. All right, so let's pick up where we left off. Okay, so let R be a commutative ring, S subring, and I an ideal. And remember, subring now has this kind of loosened. I don't demand it has an identity that's shared with R. R makes an S. If I is not equal to S, and S minus I is a union of primes, with each PI and R prime. Any guess as to what's going on here or what the conclusion can be? Well, then S is contained in P J. So then S must be contained in one of these ideals. Okay, and actually this follows very quickly from one of the results we did last time. Notice that S is contained right? Because since S minus I is contained in that union of primes, then S is contained in I, union that collection of primes. And remember that result we had about, we can give a quote here. If you have the collection of ideals, and at least n minus 2 of the ideals are prime, then S must be contained in one of them. Well, that's what we've got going on here. In fact, n minus 1 of them are prime. And so there you go. Proposition. Let A be a non-zero R module and I the annihilator of A. So I is, when I say the annihilator of A, this is just the ideal of R that kills everything in A. Notice that, of course, it's not empty because you've got at least 0 in there. If P is a prime ideal that's minimal over I, then P is contained in the 0 divisor set on A. If P is a prime that's minimal over I, then P is contained. And remember what this is. This is the collection of things that kill some non-zero element of A. Okay, let's go through the proof of this. Let S be the set of elements of the form. This is kind of a fun set. Of the form, we're going to say A, B. With A not in B and B not in CA. Note that S is multiplicative close. Right? Because if you have hopefully my notation is suggested. A1 is not in P and B is not a 0 divided on A, so it doesn't kill any non-zero element. Then this is not in P because P is a prime ideal, and this is not in ZA. So this is multiplicatively closed set, and I claim that this set is disjoint from I. And to that end, If not, then BA then BA times capital A equals 0 with some B not in ZA and A not. And A not in P. But then AA equals 0. And the problem with this is that A is in I. Which is P, which is contradiction. So we have a multiplicative set and it's disjoint from I, right? And so once again, this theme appears. So we can expand I. We can grow it up to a prime ideal. We'll call it Q that's maximal with respect to the exclusion of S. A prime ideal maximal with respect to exclusion of S, the set of ABs. So then this Q is contained in ZA. And so I is contained in Q, which is contained in P, and so Q equals P minimality. Because actually P was a minimal override. Hence, since P is Q, we have P is in Z. Okay.
What is the conclusion that Q is contained in P45?
Well, let's see here. P is minimal over I. And so what we have is here's S, set of these pairs. P is some minimal prime. I guess I will see now, can I? We know that I is disjoint from S. Have you got it? Okay. Okay, others? Okay. Let R be Noetherian. So here's a kind of result here. Let R be Noetherian. Let's let A finitely generated. Finitely generated. R module. And I the annihilator of A. If P is minimal over I, so P is a prime that contains I and it's minimal with respect to that, then P annihilates a non-zero element of A. So here's kind of the gist of what this is saying. So what you have is you have some finitely generated R module, A. A is the annihilator of all of A. So the stuff in I kills everything in A, right? Notice anything contained inside of I perhaps kills, well, can't kill more what's in A, but notice that a bigger ideal, a larger ideal, as you grow that ideal, it may stop annihilating some elements of A, right? So I annihilates everything in A. When you grow it bigger, there's stuff that drops out of A that's no longer being annihilated. If P is a minimal prime over this, then it turns out that P is is actually the annihilator of some single element, non-zero in A, right? And that's what we're going for here. Proof. First, pass to our localized P, where P is our set prime ideal. Notice that as R is Noetherian, so is R. So the localization, in fact, you don't even need to localize the prime ideal. If you take any Noetherian ring and localize it at any set, it's still Noetherian. Notice this is an R module. This I think we introduced this, but this is basically the module that looks like A over S, where S is not empty. And I think in an earlier homework we kind of outlined how this worked, right? Because basically this is an R module, right? So let me recall for you. If it's a little sticky in the old brain pan. That the way this module works is think of this as little pairs of our abstractions. Notice that this is something in A over something outside of P, something in A, something outside of P. This product is outside of P, and notice that numerator is still in A because A is an R module, right? So this is an element of A, this is an element of A. So this makes good, clean, wholesome sense, and it's an it's an RP module this way. Still outside of P, still in the R module A, right? I think when we in the homework when we talked about flatness, is when we talked about this. Yes.
You know what? That's not.
Yes, I do. I'm sorry. That's not. Right. It's always a sign of warning if you can have a zero denominator, right? Notice that notice that, AP is not zero. Why is that? Let me justify that really quickly. What does it take for A over S to be zero? This is true if and only if there exists a T in not in P, or maybe I should say T in S, such that A equals zero. So what will be the well, so the problem with this is, so this would mean T equals zero, so T is, but, well, let's see. But the annihilator of A is disjoint. Right. So if this, yeah, so if AP is identically zero, then you've got a problem here. And so let me point out that, of course, if you look at IP times AP, you get zero. That's easy to see because you multiply the numerators to get zero. And since I is the annihilator of A, IP is annihilator of A. One direction of that is very easy, and the other one is, or one containment is easy, and the other one is pretty straightforward. Now, the next step is, so what we've done is we've attempted to transfer this problem from just looking at a general Noetherian ring with the annihilator of A and pass to R localized B. And things translate, that is to say, if I is the annihilator of A down at the R level, then IP is the annihilator of a localized P at this level. So now we've kind of gone over, we've sort of simplified things, right? Because in R localized P is now a local ring, right? It's still Noetherian, and now it's got a unique maximal ideal. And the next step I'm going to do is I claim that, well, so P in the original situation was minimal over I. I claim that in my localized situation, that P localized P is minimal over I localized P. And If so, P localized to P is a prime minimal over finality. Of a localized. Right, so that's kind of our goal. And let me, of course, once again, kind of underscore the fact that P localized to P is the unique maximal ideal of R localized to P. If this is not the case, then there must be a prime ideal that contains IP and is properly contained in P. There is prime ideal strictly between so there's a smaller prime that contains IP and is inside of P localized to P. And of course, since we've localized, is necessarily of the form for some prime Q and R. And in fact, we can pigeonhole it further. In fact, you must be properly contained. So if there is a prime that we can sneak in between here, then it has to be this form for some prime properly contained in P. And I'm going to actually go a little further and say that this prime also must contain I. So, we now claim that I is contained in Q. So to this end, to show this, so let's let X be in I. See this. Suppose that X is contained in I, then the fraction X over 1 is an element of I localized to P. And hence must be a Q localized to P. So what does this mean? This means that I'm going to just write that one up back here and then kind of pick this apart. So there's an S1 times Sx minus Q equals 0, where the S's are in S, that is not a P. And Q and Q. Because this is what it means. This X over 1 has to be Q over S, right? So it means Q minus SX or SX minus Q times some other element multiply, because you need this other thing, because this might not be a domain, so you need S1 times this 0. But Q is in P. So S1 and S are not in Q either. Well, so let's look at this, equality again. The good thing about zero is it's in every prime ideal, right? Now, what have we said here? S1 is not in Q, so this product here is in Q. S1 is not in Q. So that must be the case. But Q is in Q, so SX is in Q. But S is not in Q, therefore X is in Q. So we get our desired conclusion that anything in I must be in Q. So by minimality of P, so Q equals P by minimality. So here's where we find ourselves. So it is true that P localizes P is minimal over I localizes P as we claim. So in particular, P localized P is contained in so P localized P is in the zero divisors on AP. So there must be a non-zero element of AP annihilated by PP. There is this non-zero element of AP annihilated. And we will say that this element takes on the form A1. We take this element, B, the form A1. Might ask yourself why you can do that, but we can take the element of this form. And since P localized P kills this element, we have that then we have, in fact, that SPA is 0. Some S not in P. So we can write B as SA, and I claim that P is exactly the annihilator of B. And there will be your element, there will be your element that you need. So notice that if XB is 0, then it must be the case that X over 1 annihilates A over 1. And so that means that X over 1 is in P localized P. Because it's part of the annihilator of A over 1. S1X is in P. So S1X is equal to, or is in P for some S1 not in P. And so from this, we must conclude that S is in P. And there we go. Well, I don't think there's anything too hard there. It's a bit windy, but any questions on that? Okay, I'm going to give you guys a definition here. We're going to define something called grade. Definition. For right now, we'll talk about it in these terms. Let I and R be an ideal. We say I has grade 1. We say I has grade 1. If there is a X and R, and here what I mean by that is I just mean that X is not a 0 divisor, such that I is containing the 0 divisors of the module R mod the ideal generated by X. Right, so what it means to have grade 1 is if there's a non-zero divisor X, such as when you mod out by this, or for this I, there's an X in the ring such that I is contained in the 0 divisors on this particular R module. So here's a proposition about grade 1 modules. Proposition. Let R be Noetherian, and I an ideal of grade 1. And I and R an ideal, say, of grade 1. Then I inverse properly contains R. I think we might be able to use this to give us some nice examples too. Let me give you a quick example. So let's look at this ring here, call it R. Certainly meets all our hypotheses. This is an Noetherian ring, in fact, UFP. In this case, but I think the idea driven by X, Y. Right? Now, I claim that this ideal is not a grade 1. And I'm going to do it as a consequence of proposition 6.8, and then think about the original definition as well. What is I inverse for this? Well, let me recall, this is a set of F and K, well, I called that tonight. F this is a set of rational functions that push I back into R. Notice that, of course, the inverse will contain all of R because it's a proper ideal of R, right? So, for example, 1 is in here because 1 pushes its ideal back into R. Because it's already in R, right? Now, the question you might ask yourself is there anything other than R that's in there? And the answer is no, because you need F times X right? So if you write F of XY as P1 XY over P2 XY, well, these animals here are polynomials. Right, which you can certainly do, right? You can write any rational function as a function of 2 polynomials. Then for fx to be in R, then this means that P1, so I'll suppress writing the variables down here, P2x is equal to Q1 QK. These are polynomials. Right? And let's say the GCD of these is 1. Like that. This means that XP1 equals Q1 QK times P2. Right? And of course, and you also get something for Y as well. So I get YP1 is right, YP1 is Q1 hat, QN hat, P2. Now, use unique factorization in contradiction of this, right? Notice that what you have here is XP1 and YP1 being two different products, both of which contain P2, right? That means that you have to have a common factor there between P1 and P2. So the upshot is I inverse is actually equal to R, because there's no, you can't have any proper function of polynomials that does this. So by this proposition here, certainly R is Noetherian. Here's your I here. I inverse does not properly contain R, so it's not a grade 1. See if you look at that example and go back to first principles there and see why it's not grade one. And I think this might reveal how to do it. Okay, we'll pick up there next time. Any questions? And obviously, we're not gonna have a final in this class, but